All right, everybody, we're getting rolling into chapter 4 right now, which is going to be the last chapter that we're going to cover here before the end of the first semester. We just finished chapter 3, which was a pretty darn big chapter, and the crux of chapter 3 was learning how to take the derivatives of different types of functions. In chapter 4 now, we're going to go a step further with all of that. Chapter 4 is all about applications of the derivative. Now that we've learned how to take the derivative of every function that we're going to have to know, now we're going to talk about what it is we can do with that derivative. And the first thing we cover in 4.1 really isn't too bad of a section here. It's called linearization, and actually the fuller title right here is linear approximation and applications. So the word linearization sounds like a funny made-up thing right here, but if you broke it down, it's basically taking something that is not linear and trying to make it linear, or at least make it more like a linear function. And the real reason behind that, the application of this, everybody, as we move forward, is that back in the day, when graphing calculators and even more powerful scientific calculators were not readily available, and I'm talking as recently as maybe 40 or 50 years ago, being able to use linear functions in order to come up with approximations for irrational or at least difficult to figure concepts right there was a really important application of calculus and of derivatives. Unfortunately, it's much less relevant to us today, but we still spend a little bit of time going through this. So, the first thing we need to understand today is what is meant by, and I have to be thorough with the definition right here, the linearization, that's not what I wanted, the linearization, not just in general here, but of a particular function f of x centered at a particular spot called x equals a. And all that means, everybody, the good news here is this is not anything that we haven't done before. Linearization is just asking you for the equation of a tangent line to your function f of x at the spot where x is equal to a. And in our little diagram here on the bottom, I kind of started with this right here. The y equals f of x would just be some particular curve, and it certainly could be a linear function, but that would kind of defeat the purpose. So let's assume for the time being that f of x is nonlinear. And what we have is a particular spot right here, guys, that we're going to call x equals a, defined as being the center of our linearization. Basically, that is the point of tangency, which we've been playing around with here for most of chapter 3. And really, all we're going to try to do now is come up with the equation of the tangent line that passes through that point, which would be a comma f of a. In fact, we might even want to label that. A is your x coordinate, and then generically speaking, f of a is simply going to be your y coordinate. So we know our point of tangency. We would use the derivative now to find the slope of the tangent. And from those two pieces of information, we would be able to come up with this equation right here, what we're going to call y equals L of x. And if you're not used to seeing L used very often as the name of a function, well, there's a reason for that. But the reason we're going to be using it today is because we're talking about linear functions. So we come up now with the blue original function, most likely which is nonlinear, and then the red linear function. And what we can see pretty obviously, guys, is that the blue curve and the red line are not the same function. They don't always return the same y value for a given x value. But what you can see is that they do actually have the exact same y value right here at the point of tangency. That's important to note. The point of tangency is the one point in this graph that is both on the original function, y equals f of x, and also on the linear function, y equals L of x. But what's really important is that as we narrow in on a neighborhood somewhere around that point of tangency, just roughly where I've circled there, the red line and the blue curve have almost the exact same y values. When you get a little further out to the side, they're really not that close, way out to the left and way out to the right. But towards the center of that linearization, the y values for a given x value here, for both the blue curve and the red line, are very close to one another. And so when we're talking about approximation, we can use that linear function to come up with an approximation that's usually pretty close to the true value on the blue curve. So let's see what this looks like, everybody. We're going to start off with one that I don't think is going to be all that bad. So we're going to find L of x for this given function, f of x is equal to the square root of x, and we're going to center that linearization at x is equal to 4. Now, a couple things to note here. First of all, anytime they ask you to find L of x, that means we're doing a linearization. So L of x doesn't just mean a function, it means a linear function, and specifically, it's the tangent line equation that we're looking for. Second of all, they gave you the function with an explicit definition right here, f of x is equal to the square root of x. And lastly, they told you where to center that linearization. When they do that, everybody, that 4 is actually your a value right there. Okay, so we need to know all of that. But once we kind of clear all that mess out of the way right there, we realize that this is really a problem that we already know how to do. We're being asked to come up with the equation of the tangent line. And there's two things we need to do there. First one, although this is one that people forget sometimes, we need to evaluate the original function f at this a value here, which is 4. So f of 4 is just going to be the square root of 4, which is 2. In a few slides, probably in about 5-10 minutes, we're going to start talking about choosing our own a values, where that's not going to be given to you in the problem. And one of the things you will notice is that this particular a value evaluates cleanly in this function. You wouldn't want to pick something like a equals 5, because then you end up trying to take the square root of 5, which certainly exists, but it's irrational. So you're going to want to choose your a value to be something that works nicely in the original function. So right now, guys, that tells us that our point of tangency is going to be the ordered pair 4, 2. That's one of the two big things that we need. The other thing we need is the slope of our tangent. So we're going to need f prime of 4. But before we can find f prime of 4, we better first try to figure out f prime of x. And I wonder if the derivative of the square root of x isn't something that you guys have memorized yet. I would think of this original function right here as x to the 1/2 power. So using the power rule, our derivative would be 1/2 x to the negative 1/2. So that's going to become a 1 over 2, there's the 1/2, and the x to the negative 1/2 becomes a square root of x located down on the bottom. And that's all you can do for f prime of x. And then from there, everybody, now that we know that, we can go ahead and evaluate f prime of 4 to be 1 over 2 times the square root of 4. Well, that's a 2 times 2 on the bottom. That's going to end up with a 1/4 right there. And that, everybody, f prime of 4 is the slope of your tangent. So if you look at the two things that I have boxed up, here's your point of tangency, and here's the slope of your tangent. So I think we're ready to put this thing into point slope form for starters. We would go with y minus our y coordinate, which was 2, equals our slope, 1/4 times the quantity of x minus the x coordinate, which is 4. Now, a lot of times I've told you that if they're not specific in their directions, everybody, you can really leave your answer in any form you want. But since now we're being specific and they're asking it for it in this form, L of x, that is a function notation. We need to have this thing solved for y. So what are we going to get here? We're going to get y minus 2 is equal to, we'll distribute that 1/4 and get a 1/4 x minus 1, and then we'll add 2 on both sides. So we get y by itself, but what you really want to get in the habit of right now, guys, is going ahead and saying that y is equal to L of x, because that's really the form we want our answer in. And this is going to be a 1/4 x, and then I'm sorry, I didn't write that down, but when we would add a 2 to both sides right here, yeah, we're going to get L of x is equal to 1/4 x plus 1. And that is the answer to the question that was asked on this slide right here. So find L of x for that function there at x equals 4, and we've just come up with the linearization now, the equation of the tangent line to this curve right here, y equals the square root of x, evaluated at that point of tangency there, which was 4, 2. And now, what would that be good for? Let's move on to the part B right here. We're now going to use L of x to approximate f of 4.1. Now the function hasn't changed here, guys. F of x was the square root of x. So what they're really asking us to do, in fact, let me just go ahead and write this down here. F of 4.1 means exactly to take the square root of 4.1. And as I'm sure you guys realize right now, that's not something that we can answer with any kind of certainty. I do know that the number exists. I do know that it has to be a little bit bigger than 2, but how much bigger than 2 is a total guess. So the way we're going to do that, guys, is we're going to work on this idea right here, that let's try that again, that f of 4.1 is approximately equal to L of 4.1. And let me just stop and pause right there. That second line, actually this one wasn't hugely important, but this second line that I drew right here, that's really the big idea of what we're doing in these sections and these types of problems here, guys, that if we want to find the value of f, evaluated at an ugly x value or an a value like 4.1, we can get a good approximation for that by using our linearization function. And the linearization function we just came up with was 1/4 x plus 1, if I'm not mistaken. So that is going to be a 1/4 multiplied by your x value now, which is 4.1, and then a plus 1 at the end of all that. Oh, and let's see if we can do this without a calculator. 1/4 of 4 is 1. 1/4 of 0.1 is going to be a 0.025. So I believe this is going to be a 1.025 plus 1, all of which is going to get us a 2.025. And that's our answer then, everybody. In fact, let me go ahead and write this out now, that f of 4.1, and if I'm going to do this right, I should not put equals right there. I should say is approximately equal to 2.025. Now, if we take just a moment, let's go ahead and cheat and let's use some modern technology and see how we did. We really wanted to know right here, guys, what is the square root of 4.1? So I've got my CAS open right here, so let's try this. The square root of 4.1, I think you guys know this. When I hit No, I take that back. When I hit enter on my CAS, because I put in a decimal number, it's going to give us a decimal approximation for the answer. They've got 2.02484567313, and we came up with an answer of 2.025. That's pretty darn close, everybody. We ended up with what? 1/1000th of that answer right there, or really about 2/10,000ths. So we came up with an answer that was pretty darn close to the real value here, which we wouldn't have been able to attain so easily 50 or 100 or 500 years ago. Okay, and the reason this worked is because, let's go back to this original diagram down here on the bottom. If we focused on a spot right here, we'll call that our A value. Like in this example where A was equal to 4, we were looking at what was happening just a little bit to the right of that point. And the Y value of the blue line right here and the Y value of the red line right there are really, really, really close to each other. But it was much easier to come up with the Y value from the linear function than it was from the nonlinear. And that's kind of what's happening right here. So we're really taking the equation of a tangent line and we're taking it just one step further. Now, guys, that concept right there pretty much rules the day here for the rest of this section. They try to dress things up in a slightly different way here, so we're going to go ahead and talk about this. But if you have understood everything that's happened up until now, you can actually just use that method repeatedly to try to figure the rest of this out. But the second thing that your author decides to talk about here is this concept of approximating delta f using our linearization function, L of x, which we just came up with. And if we take a look at what's going on right here in this diagram that we've drawn here, guys, let's see if we can illustrate better. I didn't label this, and I should have. The blue curve, again, everybody, is going to be the original function itself. So the blue curve that I've drawn, we're going to let y equal just your generic function, f of x, which again is pretty much always going to be nonlinear. There's no point to doing this if f of x was already linear, although the methods would work. And now what we're going to do is we're going to focus on one particular point of tangency, which I have right over here at the point labeled A. So again, I've called that A comma f of A. And what we're now doing this time, you can tell here, I think, is we're drawing the tangent line to the blue curve at the spot where x equals a, but we're now talking about another point located further on the curve somewhere, and that point I've labeled B. Okay, and if we wanted to make an ordered pair out of that, I guess you could call it b comma f of b, and there you go. And what we're working on now is finding delta f. Now, if you remember the first simple thing you learned back in Algebra 1 or Algebra 2 about function notation, it's that really f and y can kind of be used interchangeably. So what we really want to know is, what is the change or the difference in the y values between our starting point of A and our ending point of B? And that's what this vertical movement right here, basically guys, we're talking about the rise between point A and point B. Rise measures how far you had to go up or potentially down to get from point A to point B. And when you talked about it with slope, we talked about it on a linear function. Well, all right, that's what we're working on right now. And what you guys can see is that this delta y would actually be a little bit different depending on whether we wanted to know the y value on the actual curve or the y value on the linearization, the linear function located right over here. Well, what we would really like to know is this one right here. But because that's so difficult to find, we usually end up just dealing with the linearization, and that's why, once again, we are approximating a delta f value instead of finding it for real. So if you guys notice, between point A and point B, I drew this pretty little green triangle right here. And, not surprisingly, it's a right triangle, everybody. All right, and it looks something like this. And one idea that I don't think has ever been brought up for you guys before in the last umpteen years, but isn't really complicated, is that there's a way to try to figure out your rise, your delta y or your delta f, if you know a couple of other things. So let's start with something pretty basic that I think everybody is comfortable with, that the slope of that red tangent line that we've drawn is simply given to us here by delta f over delta x, or delta y over delta x. That's the basic definition of slope there. That slope of any line, including in this case your tangent, is delta y over delta x. But now, everybody, what's going to happen here is that we're trying to find delta y, which we can do if we know the slope of your tangent and you know the value of delta x. And if we knew those two things, everybody, let's take a look at how we went from this first line here down to this second line. All I did, let's go ahead and show that in purple, is I now multiplied both sides of this equation by a delta x, and I'll put that here as well. So what happened now, guys? The delta x gets multiplied by the slope of your tangent. That was my left-hand side before. And on the right side, the delta x's cancel, all right, leaving you with just the delta y or the delta f. That really was the right side over here. So that leads us to this little formula over here, guys. The delta f is approximately equal to f prime of a, which is the same thing as the slope of your tangent, f prime of a multiplied by your run, delta x. So if you know the slope of your tangent and you know the change in x, you can find the delta f, or the change in y value that you're looking for. And usually in problems like this, they're pretty explicit in what it is that they're asking for. So I got to scroll that down, sorry. So let's take a look at this one. Pardon me, guys, the spacing is a little bit weird here. But we're going to estimate delta f for this given function right here. Let me change this back to... I didn't know I could change the color of my calligraphy pen. That's kind of cool. I learned something new today. Anyway, I didn't want to. Here we go. For this function right here, f of x is equal to x minus 2x squared for an a value of 5 and a delta x value of negative 0.4. Okay, so we're going to do this. Then after we come up with an answer, maybe we'll go back and try to explain what it was that we have just found. But let's focus on directions, guys. The directions are telling us to estimate delta f. So let's not make this too complicated. We just learned a formula here. I lost it. It's at the bottom of this page. But here we go for how to estimate the value of delta f. And that's this formula right here. It's f prime of a multiplied by delta x. So let's write that down before we confuse ourselves at all. So delta f is approximately equal to, oh, that was ugly, f prime of a multiplied by delta x. So what are we going to need in order to pull this off? Well, for starters, we need f prime of a. You can't find f prime of a, though, until you have found f prime of x. So let's jump down to the side here and see what we can't do for that. F prime of x, then, is the derivative of f of x, which is located right here. So that derivative, I think we can just do using the power rule, is going to be a 1 minus a 4x. That's it. And now we're going to evaluate f prime at our given a value of 5, which is going to be a 1 minus a 20. That's going to be a negative 19. That is a very steep tangent line, everybody. But that is our value now for f prime of a being 5, negative 19. And we're going to multiply that now by the delta x value, which they gave us as negative 0.4. So let's put all that together, and I do believe, let's see, 19 times 4 is 76, so this looks like it's going to be a 7.6. And because we were taking a negative times a negative, it looks like we've ended up with a positive value. And guys, that is going to be our answer here. Delta F is approximately equal to 7.6. Well, whoopity-doo, everybody. All right, we came up with that answer, but I don't think that explains at all what it is that we just found here. So let's go ahead, and I tell you what, since I have my calculator up and running, let's go ahead and try to do this one with a real graph. I'm going to graph the original function here of x minus 2x squared. So let's go here, and let's see if I remember how to do this. We're going to add a graph here, and our function is going to be x minus a 2x squared. Okay, and we come up with a downward opening parabola that looks something like that. The spot at which we're interested in right now, everybody, was when a was equal to 5, if I'm not mistaken. Let me double check that. Yeah, a was equal to 5. So what I'm going to do is I'm going to do a trace on this graph here. I'm going to go to Tools and Trace and go to Graph Trace. And, oh boy, I'm not quite sure how to do this on here, everybody. If we drag that down a little bit, I could get close to it, but I'd really like to be able to type in this exact value, but I'm not sure how to do that on this calculator here. So nothing selected. That doesn't work. On the regular Inspire, I could just type in a 5 on my keypad and I'd be all good to go, but I'm not quite sure how to do that here. So can I just get close to it? Oh, this is not going to be exactly what I wanted, but okay. You can see we're tracing this thing pretty far down, and I'm looking at my x coordinates down in the bottom right-hand corner of my screen. I'm getting closer to it, but not quite there yet. Let's, okay, this is... Oh, well, now I went past 5. Okay, so right about here-ish. Getting pretty close to it, guys. Okay, so right about there, probably. Sure, we'll call it that. Can I go ahead and... Let's see, there's a way to do enter as we go through tap around it. Oh, double tap the trace point to enter an exact value. Hey, how long we knew that. Okay, so double tap that, and we'll put in a 5 and hit enter. And now I think if I, what did it tell me then? Long press the trace point to create a persistent point. That's what I think I wanted to do right there, was hit that for a minute, and I was hoping that would stay. Nope, it didn't stay. All right, let's try that again. We'll double tap that. We'll put a 5 in here. We'll hit enter, and then it said long press that point. Okay, and there it is. Good. So now I think we have that one point where it is where we wanted it, all right? And the other thing we wanted to deal with now, let's go back to the original problem here. Well, let's look at this. We now wanted to talk about what was happening here, the change in f with a delta x value of negative 0.4. So what that means, everybody, is that our a value was 5, all right, but the second point, kind of the point B we were looking at, is going to be located 0.4 units to the left, because it was negative, of 5, which would be 4.6. So let me go back now to this function here. See if I can shrink this down a little bit. And I'm now going to put a second point on this curve here at 4.6. Let's see if I've learned my lesson here. So 4.6, we'll hit enter. That gives us this point. And if I hold that down for just a second, okay, there we go. So this is what we have here. There are 2 points located on this curve. And what we were interested in doing in this problem was estimating delta F, the change in y in between those two problems. And what we came up with here, guys, was that our change in y was approximately 7.6 units. Well, if we take a look at these two y coordinates, we've got negative 37.72, let me write that down, and a negative 45. So let's see here, a negative 37.72 and a negative 45. And if I were to subtract those two numbers right there, the minus negative right here would just become a plus. That would get us, let's see here, everybody, a 7.28. Now that's the actual change in y between these 2 points. Our approximation was 7.6. Not super close, but within the ballpark right there. All right. So what we actually found was the change in y on the tangent line. This would be the actual change in y on the function itself. All right. All right. As I've said, guys, I think this section is maybe a little bit low in the practical applicability department right here, but hopefully we get what's going on here. Wanted to do just a little bit more with you here and show you that there's a couple of other styles of problems that you're going to be asked to look at on your homework in this section that are related to what we're doing right now. First of all, I don't like the way those square roots got typed in right there. So square root of 26 minus the square root of 25, and we're going to do that using linear approximation. Okay, so you'll notice this problem then looks different from the one that we just did, but with a little bit of translating we can get it there. First thing, we're going to try to break this down, and you'll notice that in everything that I've asked you to come up with right here in part 1 of this problem, it's now going to look pretty much like this one did in example A. So estimate delta f for what function? Well, both of these terms right here, the square root of 26 and the square root of 25, I think obviously, are asking you to take the square root of some particular number. So the function we're dealing with here is f of x is equal to the square root of x. When choosing an a value, we usually want it to be one of these two numbers right here. If not, it just needs to be a value close to those numbers. But the important thing is, and I said this earlier, a has to be a number that you can evaluate cleanly in this function right over here. So obviously, I don't want to pick 26 because I don't know what the square root of 26 is. But I do know that 25 is a perfect square. So we're going to let a equal, dang it, I did it again. We're going to let a equal 25. If I can write on this without getting my hand all over it, okay, a is equal to 25. Now, like I said, oftentimes the a value will be one of the numbers that they gave you, but not always. If they had given me what's the square root of 27 minus the square root of 26, I still probably would have chosen a to be 25 because it needs to be a number that you can evaluate easily in this function right here. And now for delta x, this isn't a choice that we get to make. You need to look at this value here and this value right here and realize that that first term, the square root of 26, well, that's f of 26. The second one is f of 25. And the change between those x values from 26 to 25 is 1. Now, if it was the square root of 28 minus the square root of 25, 28 to 25, delta x would have been 3. But in this case, it's just 1. Now, one thing I want to point out before we go any further is this. A really common mistake that people make in these problems right here is they'll do everything right, but they'll simply get the opposite sign for their answer. They'll get a positive when they should get a negative or vice versa. So the one thing that I want to point out to everybody is this. If we went back and looked at the original expression, what is the square root of 26 minus the square root of 25? Simply ask yourself this question. Should this answer be positive or negative? You can usually tell just by looking at it. Well, the square root of 26 is going to be greater than the square root of 25, so this answer should be positive. If we end up with a negative, the mistake we made is probably coming from right here, and it probably means the delta x should have been a negative 1 rather than a positive 1. Let's not worry too much about that right now. Let's just remember now that this answer needs to be positive. Okay, so what's next, guys? That's really it for that. We're basically just translating the question here. Okay, and I left myself some room, but let's go ahead and let's keep doing what I've written out here in part 2, although now that I think about it, I feel like I could move all this up and save myself a little bit of space. So now that we know all of that, or should I have done that before? I guess I left myself some room there. Let's go ahead and do what I had written down here before, guys, which was to estimate that delta F value. So what have we learned here? That delta F can be approximated now by taking your F prime of A value and multiplied by delta X. So we've got to do a little bit of work here, guys. We know that F of X is the square root of X. So F prime of X, this is the second time today we've done this now, is going to be 1 over 2 times the square root of X. Again, if you don't have that derivative memorized yet, that the derivative of the square root of X is 1 over 2 root X, that might be something that you want to commit to memory pretty soon. And now we can go ahead and evaluate F prime at our A value of 25. So what's that going to do for us, guys? Down in the denominator, the square root of that 25 becomes 5. It gets multiplied by 2 to make a 10, so the slope of our tangent here is 1/10. All right, so let's keep going here, guys. Delta F then is approximately equal to F prime of A, we just estimated to be 1/10, and we're going to multiply that by delta X, which is 1, so we're going to come up with this delta F value right here of simply 1/10. Okay, and with what we had written to do here, estimate delta F, okay, that's our estimate then for what the change in Y would need to be. Now we did say, let's think about that everybody, should this answer be positive or negative? As we go back and think about the original expression, we said it should be positive, and this one is. So that's good. Okay, what's next then? The second thing that we had written down right here is we're going to find L of X of that particular function here centered at your value there. So what's going on here? This is kind of like two different variations on the same question, or maybe two different ways of doing it. Okay, yeah, I think I remember what I was going on. So we're going to get the same answer here on part 2 that we got in 1. But if we thought about this, let's go ahead and I'll show you what I meant here. The function was the same. It was still going to be the square root of X centered at the same A value, which was going to be 25. So if we thought about how to come up with the equation of our tangent line. Let me start a new page here. Actually, you know what? Nope, that's not what I wanted. I'm going to steal all of this and just move it onto a new page right here, guys, because we don't have room here to do that. So I'm going to cut, start a new page, and then we'll paste this sucker right here. Okay, so this is kind of the alternate way to do this one if you didn't want to learn that new formula here. So this is going back now to what we had said a moment ago. I can't get rid of all these boxes. There we go. All right, of trying to come up with the equation of our tangent line. So the first thing we'd probably want to do is evaluate F at the A value in question, 25. Well, F of X was the square root of X, so that's just the square root of 25, which is equal to 5. And that means that our point of tangency is the ordered pair 25, 5. What else? We need to find F prime of 25. Well, on the last problem, or the last page, we wrote that F prime of X was 1 over 2 times the square root of X. So that's the square root of 25. Yeah, we did this work already too, guys, and that's 1/10, which is the slope of your tangent. So if we now wanted to go to point slope form, we've got our tangent line equation of y minus 5 equals 1/10 times the quantity of x minus 25. From there, we would have y minus 5 is equal to, we could distribute here and get a 1/10 x minus 25 over 10. We could divide a 5 out there and get a 5 over 2. And then we could just add 5 on both sides. And we would get y, which is the same thing as L of x now, is going to equal a 1/10 x minus, and let's see here, guys, adding a 5 on the left would be the same as adding a 10 over 2 on the right. So a negative 5 over 2 plus a 10 over 2 is going to be a plus 5 over 2. So there's your linearization function right there. Now, how does that help us? What we were really looking at doing here, guys, is coming up with an approximation for the square root of 26. So let me switch colors on you here now. I'm going to go blue, and we're going to say, draw a little line right here, that the square root of 26 is approximately equal to, well, let's put a 26 into this function right here. That's going to be a 1/10 times a 26 plus, I'm trying to think if I want to do that as a fraction or a decimal. I'll keep it as a fraction because that's how we had the last answer right here. So that is going to become, let's see here, guys, 26 over 10 is going to be a 13. No, you know what? That was dumb. Let's keep that with a 10 right there on the bottom. So that's going to become a 26 over 10 plus the 5 over 2. If I multiply the top and the bottom by 5, that gets me a 25 over 10. So the square root of 26 is approximately, looks like a 51 over 10. And now we came up with a fractional approximation for the square root of 26. The real thing we were being asked to find here, guys, if we go back to the beginning of this problem, is what's an approximation for the square root of 26 minus the square root of 25? Well, the square root of 26 we approximated to be 51 over 10 minus the square root of 25, which is just 5, or 50 over 10. And the 51 over 10 minus 50 over 10 is going to get us 1/10, which, of course, you will notice is the exact same answer that we came up with doing the problem the original way here with the 1/10 right there. Now, I definitely think as you look at these two side by side, I definitely think this first method right here, using this formula, was a lot easier and a lot more succinct than just using the linearization here. So that's part of the reason why I think that that formula that I just underlined here, I'm sorry, right here. Okay, I've completely lost it. All right, here we go. This formula down on the bottom here, guys, that this formula is worth learning rather than just doing the linearization method there, but I'll kind of leave that up to you guys. And the last thing I want to do with you here, guys, and then this is the last section here, is trying to find, that's another bad formatting here, is trying to find just another application or another different way of writing really the same concept right here. If we're trying to find 1 over the square root of 18. Now you'll notice the directions right here are back to just approximating a value. They're not asking you to find a difference per se. So in this case right here, I'd probably do this one, maybe the second way that I had talked about doing the last one right here. I don't think the delta f really applies. All right, so what I think we want to do is I think we want to come up with a function right here, which we're going to call f of x. I think we want to come up with an a value. And then I think from there we can just come up with the equation of a tangent line. So 1 over the square root of 18, that's kind of ugly, but I think the function that most closely matches would be 1 over the square root of x. And the a value that we would want to choose would be a value that's close to 18 right here, but that works nicely when we plug it into the original function. I need a perfect square, guys, and the perfect square closest to 18 is going to be 16. Okay, so with that in mind, that really should be everything we need to come up with the equation of a tangent. First thing I would probably do is f of, there it is again, okay, is f of 16, which means we're going to do 1 over the square root of 16, which is just going to be a 1/4. So our point of tangency is the ordered pair 16, 1/4. Okay, next thing we're going to need, so that's a big one right there, next thing we're going to need is slope of the tangent. And you can't find f prime of 16 until you have first found f prime of x. So, to take the derivative of this function right here, we should probably think about rewriting that real quick. That f of x, it's a square root on the bottom, guys, so that's going to be an x to the negative 1/2 power. The derivative of that then would be a negative 1/2 out in front times the same base x now to the negative 3/2 power. Okay, and I'm trying to think if we should simplify that at all. Yeah, let's go ahead and do that. The negative 1/2 is going to put a negative out in front, a 1 on the top, and a 2 on the bottom. And some of you guys are still making this mistake. I see it on your tests and your quizzes here, that when we're taking x to the 3/2 power, the denominator of that fractional exponent, which in this case is 2, that becomes the index of your radical. You don't need to write that 2 there, but then the numerator becomes the exponent right there. So it's the opposite of 1 over 2 times the square root of x cubed. And now we need to evaluate f prime at our a value of 16. So where are we here, guys? A negative 1 over 2. And remember, in a case like this, you actually have the option. What I'm going to do here first is take the square root of 16 and then cube that result. You could do 16 cubed, which is a really big number, and then take the square root of that, but it's easier to go this route first. Square root of 16 is going to be a 4, and 4 cubed is going to get us a 64. So the slope of this tangent looks like it's going to be negative 1 over 128. So now that we know the slope of our tangent and we know the point of tangency, we could go to point slope form. And I think I'm going to need a new slide in order to do this. So in point slope form, it looks like it's going to be y minus our y value of 1/4 equals your slope, which I think was a negative 1 over 128, times x minus your x value at your point of tangency, which was 16. Let me double check all of that. So 16 1/4 was the point of tangency. Slope of the tangent was a negative 1 over 128. Okay, that's where we are right now. All right, and we want to try to get this thing solved for y. So I'm going to go ahead and do something you've seen once or twice before. I haven't done it very much. I'm not going to bother because distributing the negative 1 over 128 is going to be really ugly when I get to the 16. I'm going to do this, that y is equal to, and let me go ahead and call it my linearization function, L of x, and I'm going to go to point slope equation, everybody, which is a cheap version of slope-intercept form. Actually, it's a cheap version of point slope form, but you do it when the distributing wouldn't really help and you'd end up with a really messy spot anyway. So I'm going to leave this right side the way it was, looking like this, and then just add the 1/4 at the end of that. Technically, we have solved for y. It's just kind of a cheap way to do it. So there's your linearization function. And what we really wanted to know in this problem, everybody, is what's an approximate value of 1 over the square root of 18. Okay, so what we're really going to do now is evaluate our linearization function at that particular value right there of 18. All right, that's what's going on here. So 1 over the square root of 18 would be approximately equal to L of 18. That's the whole point of coming up with the linearization function. So what's that going to look like? Negative 1 over 128 times our x value is now an 18 minus 16 and a plus 1/4. All right, let's see where this gets us to. So that's approximately equal to, all right, that looks like it is going to be, okay, we've got a 2 right here, and a 2 times a negative 1 over 128 is a negative 2 over 128, or a negative 1 over 64, ugh, not fun, plus a 1/4 at the end. Well, let's go ahead and get a common denominator. 1/4 is going to be a 16 over 64, and that looks like it's going to get us a value here, this could be worse, of 15 over 64. Now that, everybody, should be a decent approximation. Let's go back to the calculator and cheat now a little bit and see what we've come up with. The real thing we were looking for was the value. Let me get out of here and go back to where we were a second ago. How do I get to, yeah, here we go. All right, so the real thing we were interested in knowing here is what is 1 divided by the square root of 18. And well, that's not really what I wanted. Let me do a long press there. Okay, and an approximation of that answer. Okay, so using a calculator, that answer is 0.2357, yada, yada, yada. We came up with, for our approximation, 15 over 64. So if I were to just type in 15 divided by 64, and let me learn my lesson now and go right to the approximation, this is what we came up with, 0.234375. Those two answers look pretty similar to one another. Okay, are they exactly the same? No, but they're not supposed to be. That's the whole point of doing an approximation, but they're close enough right here, guys, that I feel pretty comfortable in the answer that we came up with. All right, guys, that's a wrap on 4.1. To be honest with you, not the most relevant and useful section here of everything we're going to do moving forward, but hopefully that gets you through this. So good luck on the homework, and let me know if you guys have any questions as you're going through it.